Hello, let's discuss an integration technique known as integration by substitution. This is section 6.6. The method of substitution can be thought of as an anti-chain rule. So here's what I mean. Let's consider a function, big F of x, which is a composition. It's little f composed with g. To take the derivative of big F of x, we need the chain rule. It says big F prime of x is equal to little f prime of g of x times g prime of x. So if you think of little f as the outside function, little g as the inside function, chain rule says take the derivative of the outside, leave the inside alone, and then multiply by the derivative of the inside. So what we want to do now is go in the reverse direction. Let's start with this thing here on the right-hand side of the equation and find an antiderivative. In other words, let's find something whose derivative is this. I've drawn a little schematic to illustrate the process. It's a 5-step process that looks something like this. So let's start with the integral of f prime of g of x times g prime of x. Step 1 is to look for a g of x, g prime of x pair. Once you identify this pair, step 2 is to let u equal g of x. And once you've made this substitution, letting u equal g of x, you need to compute the differential du, which is simply the derivative of g of x, g prime of x, with dx attached. Step 3 is to do the substitution. So if you go back to the original integral, replacing g of x with u gives us f prime of u, and then we still have this g prime of x dx left over, which gets replaced by du. So doing the substitution gives us f prime of u du. And notice now the integral involves only u's. There should be no x's left over if you've done this correctly. Step 4 is to then find an antiderivative of f prime. And the goal is for this to be easy. That's the whole point of doing the substitution. You should now have something here whose antiderivative is easy to find. And finally, step 5 is to get back to all x's, the original variable. So we plug in u equals g of x, giving us f of g of x plus c. And there you have the antiderivative. Let's try a few examples. We'll start with this one. Evaluate the indefinite integral 5e to the 5t plus 2. So thinking back to that schematic, the first step is to identify your g prime pair. In this case, we're using t as the independent variable, so we're now looking for a g of t, g prime of t pair in the integrand. And a lot of times when you have e raised to a power like we have here, you take g of t to be that thing raised to the power, or that thing in the power, I should say. So we're going to let g of t be 5t plus 2, and then g prime of t, the derivative of this thing, is 5. That's also part of the integrand. So there's our g prime pair. Step 2 is to let u equal g of t, which in this case is 5t plus 2. Then we compute the differential du, which is simply the derivative of g. Derivative of this thing is 5, and we attach the dt. Step 3 is to do the substitution. So I've got the original integral here. I'm going to replace 5t plus 2 with u, giving me e to the u. And there would still be left over this 5 dt. But notice that's what du is. So the 5 dt gets replaced with du, and we have the integral e to the u du. The next step is to do the integration, find an antiderivative. Well, we know an antiderivative of e to the u is itself, so we end up with e to the u plus c. And the last step is to get back to the original variable t, so I'll now replace u with 5t plus 2, and there's our antiderivative. Here's another example. Evaluate the indefinite integral x times the quantity x squared plus 3 squared. Step 1 is to identify a g of x, g prime of x pair. In this case, we'll try letting g of x be x squared plus 3, the thing that's raised to a power here. And its derivative would be 2x, which doesn't match what's left over in the integrand exactly, but since we're only off by a constant multiple, we're okay. And I'll have more to say about that in a moment. So we're going to let u equal x squared plus 3. Then you compute the differential du would be 2x dx. And as I said, this differs by a constant multiple from what's left over in the integrand when you replace the x squared plus 3 with u. So you notice we'd be left with an x dx. And that's okay, that's part of this expression for du. We have the x dx here. Let's just divide both sides by 2, giving du over 2 equals x dx. So now we're ready to do the substitution. I replace x squared plus 3 with u, so we'd have u squared. And the x dx that's left over gets replaced with du over 2. Now the constant 1/2 can come out, and we're left with 1/2 times the integral of u squared du. So that's something we're comfortable integrating. We end up with 1/2 u cubed over 3 plus c. And the last step is to get back to the original variable x, meaning we need to replace this u with x squared plus 3. And so there's our antiderivative. I have one more example to look at, and this involves a definite integral as opposed to the indefinite integrals we looked at earlier. So we want to evaluate the definite integral from 0 to 3 of 1 over the square root of t plus 1. The logical choice for u here is t plus 1. And if that's what we choose u to be, then du is equal to 1 dt, which I could just write as dt. So we have a couple of options moving forward. Option 1 is to leave the leave the limits of integration alone. So we're going to leave this lower limit 0 and upper limit 3 alone. I'll replace t plus 1 with u, giving 1 over the square root of u, and we replace dt with du. Before trying to integrate, let's rewrite the integrand as u to the negative 1/2 power, and then we can integrate getting u to the 1/2 over 1/2, and I'll use our vertical bar from 0 to 3. But before you try plugging in these limits, 0 and 3, you need to get back to the original variable t. So now I want to replace u with t plus 1, and we can then evaluate this thing at 3 and subtract this thing evaluated at 0. So plug in t equals 3 and t equals 0. This reduces to 4 minus 2, or 2. The other option is to convert to new limits of integration. So we're making the substitution u equals t plus 1. And you can see here I've written when t equals 0, so this is that original lower limit of integration, u equals t plus 1, or 0 plus 1 equals 1. And when t equals 3, that's that original upper limit of integration, u equals 3 plus 1 equals 4. So I can now do my substitution and use these new limits of integration 1 to 4. So in this case, we find our antiderivative, evaluate from 1 to 4. We do not convert back to the original variable t. So I leave this as u to the power 1/2, and plugging in u equals 4 and u equals 1, we end up with 2, which matches what we found earlier. So you can decide which option is best for you. See you next time.